The next optimization technique is called function inlining. The idea is to place a function call with the body of the function itself, just like a macro does at the preprocessor stage. Now, there are two implications. One is that it avoids the function calling overhead, basically saving the context, because ARM procedure calling standard expects the caller function to preserve certain registers which may be reused in the called function. So that is one overhead, and of course upon return it has to pop them back. That's a significant overhead. So if the function call itself is avoided, this context saving can be avoided as well. Now this works fine if the called function is not very big, like in the case of this swap function here. It just does two assignments here. And if the number of times this swap function is called is too much in the main application, then the code size will bloat that many times. So it has to be used judiciously, and all it does is basically avoid the function call overhead. Let's look at this code here. So this is equivalent to this function call is the x and y are the global variables with which it is called. So it is basically these two operations are directly inlined and there is no function call. So this is the transformation that happens here. So an additional advantage is that placing the function code inline exposes it to further optimization, such as enhancing performance and more. So here is the same code of a main function calling swap, and here is the swap function's implementation. Let's look at what the optimizer can be set to. So we have chosen the highest level of optimization with only function inlining selected. Now let's compile this. So it's compiled. Let's load it. And here is basically the disassembly code, and these are the variables which are initialized. X equal to 2 and y equal to 5 are there in the watch variable window at address 0 and 4. Here is the function, main function. As you can see, there is no call to swap here. So the registers are loaded with the values, and then a move operation. So basically the store operation directly handles the swap. Let's execute this and so you can see that the value have been exchanged. So the idea is that the function call is completely eliminated, even though this is the corresponding source code here. The target code does not have a function call, which is a branch and link instruction. You instead see directly the load and store operations, which basically accomplishes the swap operation. So we saw the swap function being inlined out. Let's look at a slightly more complex function. Here you have the main function calling factorial fact1 with an argument unsigned value 3. So 3 factorial is what you want to compute. Here is the body of the function fact1, where it's basically just a typical downward counting loop, and the product is computed here and returned. Now, as you can see in the disassembly code, so the value 3 is loaded, but the function itself is not called. It is actually all the multiplication and the loop operations are now part of main itself. There is no function fact1 being called here. So whatever you see, the check for the loop termination, etc., is all happening here. So you can see the source code here, branch or not equal. And here is the multiplication operation with the for the which is basic for the factorial computation. So there is no function call here. Here is a recursive version of the factorial computation. So it's the same, similar to the iterative version, except that the implementation of the factorial is a recursive function which calls itself. Now we have set the same high-level optimization and selected only the function inlining option. Let's see what kind of code gets generated. Let's compile it. So the build is done. Let's download it. So here is the main function. Interestingly, you see that it is very different from the iterative version, even at the main itself. So you can see that it is storing some register, preserving it, and then it is actually calling this function fact1. So branch with link fact1, and fact1 is basically doing the recursive version of factorial computation. We can execute and see. So it's going to factorial function where it is computing the multiplication. You can see the multiplication also here. So essentially it is basically not optimized the function by inlining it. So there is a challenge to recursive functions being inlined. Of course, there are some compilers which are capable of doing. This being non-commercial version, this is an evaluation version, perhaps it's not supported. But there are most top of the line compilers can do it, but it is not an easy thing. So the point of this example is that the same function inlining may or may not work. The compiler's ability to inline will depend on whether it's having any recursion or other restrictions like the usage of globals and so on.